Hello, my name's Julian Edgar, and together with my wife Georgina, this is our house under construction. So let's have a look at it, the Edgar Passive Solar House. So the aim of the house was to build a comfortable, energy-efficient home at almost no greater cost than a volume-built home. So not comparing it with a specialised architecturally designed home, comparing it with a normal, off-the-shelf, volume-built home. So we wanted the cost increase to be so minor that it really didn't matter, something like 5%. And so far we've achieved that. So let's have a look at how we did that and how the house actually performs. So there are basically these different areas that you need to look at if you're going to build an energy efficient passive solar home. Orientation is the direction the windows face, and you want most windows facing north. Now on this plan, north is unfortunately downwards. It's not at the top of the plan, and all the way along this front northern face we have lots and lots of glass windows, sliding doors, glass windows and so on, to get all the winter sunshine into the house to keep it warm in winter. Now the next on that list is shading. If you want the sun coming in winter, you obviously don't want it coming in summer. And so all the way along this northern face where my mouse is, we've got an eave overhang that blocks that sun coming in summer. Now, unusually, we've also got some other shading that we've used. So the eastern deck is 5 meters wide, and that stops summer sun coming in even quite early in the morning. It comes in through these windows here and this door only for about an hour or 3/4 of an hour in summer, and then it's shaded. And at the other end of the house, the western sun, the late afternoon sun, we've got a deep porch, and we've also got a panel there which stops the sun coming in from this angle, which it does late in summer. So that's orientation, that's shading. What about thermal mass? Thermal mass is the ability of something inside the house to absorb heat or absorb cool. And we have our major thermal mass is the concrete slab, which was designed according to what the engineer wanted. This is a cut and fill site, so he wanted quite a strong slab, and it was built according to those specifications. But it also stores heat in winter, that sunshine that's come in and warmed the house, and it also absorbs heat in summer, which keeps the interior of the house cooler. Insulation is obviously important. But these days, with the required energy efficiency regulations, standard insulation is fine. This house has R2.7 insulation in the walls, has R5 insulation in the ceiling, and in these two end rooms, which have tall raked ceilings, it's got 2 levels, 2 layers of R5 in each of those ceilings. Now, importantly, the slab is edge insulated, but it's not insulated underneath. Ventilation, and I forgot to put the bullet for it, but that's okay. Ventilation, really important. You can get a lot of airflow through the house in summer to get rid of that heat that's been stored in the thermal mass, typically opening the house at night. We're in the Canberra climate zone. And so all of these doors across the front can open for ventilation. That door can open, and we also have a special ventilation system that I'll cover a little bit later in this video, a convectional ventilation system that will work even if there's no wind. Finally on the list, zoning. You want on the northern side of the house to have your living areas, and so we have literally the living area there, and that room extends the full width of the house. We have bed 2 on the north. We have what we're calling the common area. Now the common area joins to a wide corridor that goes right down the middle of the house. We're calling that the gallery, and that allows that heat and light to extend right down the middle of the house as well. We have my home office on the north, and then in this house we've got a large library, and the reading area is on the north as well. And on the south, where it doesn't matter so much about how the temperature is maintained, we have the bathroom, we have the ensuite, we have a storeroom, and we also have the master bedroom. So the house has been zoned as well. So those things, orientation, shading, thermal mass, insulation, ventilation and zoning, are all really important in making this house work. Much more important, in my opinion, than the level of insulation or the windows or things of that sort. They are important, but this is more important, especially if you are watching money. So the house is built completely with conventional construction. Excuse me. So just a normal timber stud frame, normal width, not wider for extra insulation or anything like that. The frames were made off-site by a specialist framing company, Oxley Frame and Truss, who are absolutely excellent to work with. And it is all completely conventional construction, conventional ColourBond roof, conventional concrete slab, as I say, conventional timber framing, conventional timber trusses, and so on. And again, that's really important if you want a good energy efficient home, which also doesn't cost a lot. Very easy to specify more complex construction techniques that make the price go up hundreds of thousands of dollars in the blink of an eye. So I mentioned thermal mass. Here's the concrete slab, and you'll see, if you look closely, around the edge of the concrete slab it has been insulated. It's been insulated with 75mm XPS insulation, which is designed for this sort of application. The insulation was actually placed inside the formwork, and the concrete was poured against the insulation, which made it really easy to install it and again kept costs down. And it's important the edge of the slab be insulated, because that's where most heat gain and loss occurs in a concrete slab, where it's directly exposed to the outside air. Now, as I said earlier, this slab is not insulated underneath. It's what's called a ground coupled slab, connected to the ground in other words, and that's pretty important also in its performance. So this concrete slab's got lots of piers that go down underneath, poured piers, because it was on, as I say, cut and fill. And whenever it was on the fill part, where soil had been placed, the engineer required these heavy, big piers to go right down to what was the original soil level, or a bit lower than that. So standard concrete slab with piers and with beams poured within it, all exactly as required by the engineer. But in this house, it also performs that really important function of storing heat and storing cool. We've also got, unusually in this house, thermal mass that's provided by water in tanks. Water is really good as thermal mass because it quickly absorbs heat, and because it circulates within the tank automatically by itself, thermosiphons, and it takes a lot of energy to change the temperature of 1 litre of water or 1 kilogram of water. And we have 2 big tanks in our house. The house is yet to be finished, as you can see by the floor here, but we've done a little bit of interior decoration to see what it would look like. That's all Georgina's prerogative, not mine. This tank, it's a normal ColourBond rainwater tank. It has 2,000 litres of water in it, just sits there. That's 2 tonnes of water, and that water absorbs heat when it's hotter inside the house than the water, and if it's colder inside the house than the water, it gives back heat. So it acts as a thermal flywheel, if you like, knocking off the peaks, knocking off the troughs, and compared with the concrete slab, it reacts more quickly. We've got a tank like this in the lounge room. I've got another tank like this in the library, and in my home office we have a smaller tank that's actually positioned directly in front of a northern window, so that also acts as a solar collector in winter. And as I say, they're standard ColourBond tanks, so they're quite cheap to buy. I've made a timber top for that one, which I think looks fine, and of course it's functioning the whole time. You don't have to do anything, it just works by itself. So the house was built with completely normal trades. As I said, I'm an owner-builder together with Georgina. Doesn't mean we did all of the building of the house. We employed trades for the specialist jobs. So here, Adam and Harry are putting on the external cladding, just standard hardy plank linear cladding. Nothing fancy in any of the materials in the house. You can see that they're attaching it to battens, which gives an air gap behind the cladding, and down the very bottom, which you can't really see, there's a gap so air can flow in, and at the very top, which hasn't yet been done, there's another gap so air can flow in the bottom out past the cladding, or out behind the cladding, and then out past the eave. So it's a fully ventilated cavity, which is good for reducing condensation, and also it keeps the cavity cooler in summer, especially when the sun is shining staying directly on the wall. I've actually measured the airflow going into the gap at the bottom, and it's in full summer sun, and there's a measurable movement of air as it's circulating around, keeping the cavity cooler. The ceiling material is just off-the-shelf vapor permeable wrap. It's not anything special, and it was just overlapped, sometimes taped, as you can see there, but typically overlapped as the manufacturer specifies. So this is not a hermetically sealed house, deliberately so. I wanted natural flow of air to come in to allow breathing. I didn't want to have to use an expensive ventilator, or even more, a heat recovery ventilator. And so far, based on the measured performance, it looks like it's working pretty well. The CO2 level, the carbon dioxide level inside the house is absolutely fine in all conditions, and yet it still performs well thermally. So it's the right mix of having sufficient airflow that you get good breathing quality air, but also sufficiently sealed that the house interior temperature is not going up and down, where you don't want it to. The windows, you can see here some of the sliding doors. They're just off the shelf thermal heart windows from our local supplier. So they're thermally broken aluminium, but my point is that I'm making, they're not special, exotic, triple glazed or imported from Europe or anything like that. Windows can become a very, very expensive part of a house. So using off-the-shelf standard thermally broken double glazed is really cost effective. The roof you can see there is just standard Colorbond. It's got that little layer of insulation underneath it with the foil, but no more than that. It's just standard. And of course the whole shape of the house is a simple house. It's a simple rectangular house. That works well with its east-west long axis, so it can face north, but importantly it also makes it much cheaper to build. So putting on that roof is dead easy. It's just exactly the same as putting the roof on a shed, and therefore in terms of labour and in terms of time it's much cheaper than a roof with lots of hips and valleys and gables and things of that sort. So the actual fundamental design of the house was also aimed at keeping the cost low, if any house can be classed as being low in cost these days. So it uses a convectional ventilation system. So I was very concerned that I wasn't going to be able to get enough airflow through the house, especially on summer nights, to cool the thermal mass. And so I developed this system, and it's based on a system in Derek Wrigley's book. He's got an excellent book. He's now deceased, but the book that he wrote, it was really very, very good. And he uses ceiling hatches as ventilation hatches. In our house, we've got 2 in ceilings, and we also have 2, as shown here, in the end walls of those rooms that have got tool rake ceilings. So behind this vent, it goes straight through into the ceiling space. Now the vent is closed by a damper, and that damper is operated by a wall switch. And here's the rear view. You can see there's an insulated panel, a panel insulated with XPS insulation, and it's hinged down the bottom. You can't see the hinges. And at the top, you've got a 12-volt linear actuator. So you flick the wall switch, and the actuator basically opens the damper until it's sufficiently open that the air can flow through that big vent. Now that air flows into the roof space, and removing air from the roof space is this big ventilator. Now it's got a 600mm throat, so it's really quite a large one. It's an industrial ventilator. It's also powered. I've got a wall switch with a control knob, and I can turn it on and change its speed. And so if it's dead calm on a summer night and I want to get rid of the heat that's accumulated in the thermal mass, I can open the vents by flicking those wall switches. I can open a few windows, or all of them, and then I can turn on the ventilator, which draws air out of the roof space, which is also a loft, which then draws air through these vents, which then draws cool air in through the windows. And very often you don't need to turn the ventilator on. You've still got airflow that goes out through the ventilator. And I know that because I'm logging nearly every aspect of the house. I'm logging 24 different parameters, and one of those parameters that I log is airflow out through that ventilator. So a convectional ventilation system, which is very effective because it works even when there's no wind and you want to get air through the house. That's one of the things that increase the cost of the house just marginally, as I say, maybe 5%. And I made those dampers and so on. It's all pretty straightforward, but of course the industrial ventilator costs more than a normal ventilator and so on. So how well does it perform? This is where the rubber hits the road. You'll often hear people talking about how many stars their house is or how it's always comfortable. But if you're actually logging a house and you can see its performance, and in this case with no heating and no air conditioning working, then that really shows you the truth, shows you the reality. Now, we're not living in the house full time. The house that you've seen is just across the road from our current house, so it's really easy. We often stay in the house overnight. I'm operating the house as if I'm living in it, but we're not in it 24 hours a day. So cold weather performance is an example of some of the logging. In 2025, in spring, it says heat, but it actually means cold. Outside, it was 0 degrees Celsius, frost, Canberra climate. Inside it was 18.5 degrees, and that's pretty typical. It's typically 18, 19 inside. When it drops to -6, which it does here, it will drop a little bit below that, maybe 17.5. But gee, if you come in from outside where it's -6 and it's 17.5 or 18 inside, it feels absolutely delightfully warm. And one reason it feels so good is you're surrounded by that thermal mass, which has that warmth in it. Remember, the water tanks will be warm compared with the air temperature. The concrete slab floor will be warm compared with the air temperature, and so on. So you're actually surrounded. Georgina calls it your snug. You're surrounded by this snug house because it's got warmth all the way around you in cold weather. Hot weather performance, we had a really strong heat wave this past year in summer 2026. The house performed extremely well. The highest I recorded outside at the house location was 44.7 degrees, and inside on the afternoon of that day it was 24.9, so under 25. Now it did hit 27 degrees. If you look at that graph really closely, you'll see after about 6 days of very, very hot weather, including hot nights, it did hit 27. And at that point, we would have turned on an air conditioner if we weren't testing the house. We do have a single reverse cycle air conditioner, but that was only 1 day. So it's only ever exceeded 26 on 1 day, and that was only for about 4 hours. So it's doing pretty well. So typically on a day where, if I pick here, for example, it's 40 degrees, the maximum inside the house on that day was 24. Okay, and that's measured at 10-minute intervals down to 0.1 degrees C. So it's pretty accurate in terms of what's actually being measured. So far, the house is showing itself to have very, very good hot weather performance, and that's partly because of the ground-coupled slab can put heat back into the ground. And we haven't had a full winter yet. I'm looking forward to seeing how it performs, but certainly in spring when it was down to 0 degrees outside, it still performed very, very well inside. So that's the house. There it is before I'd finished painting the western end wall and before the roof got put on the porch. It's located on a rural property where we could obviously orientate it the way we wanted. It's actually orientated 25 degrees east of north because of the view that we wanted to get. And so far it's performing very, very well. In fact, it's performing better than I expected. It was NatHERS modelled using the software. I did a lot of modelling. I learned to use the software and I did a lot of modelling. But when I first put it in, it was 8 stars. And when I finished, it was still about 8 stars. But I did a lot of tweaking, like, do we need more insulation in the walls? No, it's not worthwhile doing, not from a cost point of view. What happens if I increase the window size in my home office, and so on. So this year, it's a video-only tour, as you've seen. Hopefully next year, we'll be able to open it for people to come through because I'd very much want to share what we've done with this house. Georgina and I are working on its design and obviously working along with tradespeople on its build as well. Thank you.